Good morning, good afternoon, good evening. Welcome back to Chapter 6. Chapter 6 is about cellular respiration. Chapter 6 is about burning up food molecules to get energy out of them. We know that we just got done burning up a molecule of sugar, and we know that we don't only just eat sugar. We eat other food molecules too, like carbohydrates, proteins, and lipids. Carbohydrates and proteins will each give us 4 calories per gram. Lipids, fats, give us 9 calories per gram, and that's what makes fried anything taste good. Fried anything tastes good because it's full of fat, ounce for ounce, gram for gram. You get more than twice as much energy from lipids, from fats, as you get from either carbohydrates or proteins. So that's why we love fatty things. That's why we like potato chips. That's why we like donuts. All right. Any simple carbohydrate, and simple means single sugar grain. Any simple carbohydrate can enter at step 1 in cellular respiration. It does not just have to be glucose. It can be really any simple sugar. If it's a complex sugar, we cut it up into simple sugars, and then those simple sugars enter at step 1. And then you just do the whole process that we've already talked about. It enters at step 1. Complex sugars are converted into simple sugars. Fats are sliced up and converted into something called, they're sliced up into acetyl-CoA. Thought I had a picture. All right, so if we start with a normal fat like a triglyceride. Triglycerides start with a glycerol top molecule and then have fatty acids that come down off of them. A bunch of legs, a bunch of carbons all attach to each other. Okay, so this is a triglyceride. To burn this thing up, the first thing I do is I cut the fatty acids off of the triglyceride, off of the glycerol. The glycerol then I can just turn into acetyl-CoA and send it into Krebs cycle. Once we can convert it into a product that we have seen in cellular respiration, that's where we start. All of these carbons that are these fatty acids, I convert them into 2 carbon chains. If I have a 2 carbon chain, what do I need to add to it? I just need to add coenzyme A. And once I add coenzyme A, I can just send it right into Krebs. And how many 2 carbon chains can I make out of one of these fatty acids? I can make a whole bunch of these 2 carbon chains. This is why bacon tastes good. This is why fried chicken tastes good. This is why fried anything tastes good, because of the amount of energy. Every single acetyl-CoA, remember, when you run an acetyl-CoA through Krebs cycle, I get 3 NADHs, I get 1 ATP, and I get 1 FADH2. Every single one that I run through Krebs cycle, I get this. Those 3 NADHs are worth 9 ATP. The 1 ATP makes it 10. The FADH2 makes it a total of 12. Every single acetyl-CoA is worth 12 ATP. So what's 12 times 12? 144. So 1 molecule of a fatty acid is worth like 5 times as much food as 1 molecule, 5 times as many ATP as a molecule of sugar. So molecules of fat are worth a lot more energy. When we look at these different food sources. Any kind of a carbohydrate, a sugar, enters directly at glycolysis. Fats I cut up into that glycerol and that fatty acid. Those fatty acids are converted into acetyl-CoA, and then they just they enter the chain right there. Proteins are a more complicated matter because remember how a protein is built. The way a protein is built is that I've got those amino acid things. I've got those amino acids. What's down here at the R makes a difference as to what I can do with any given amino acid. Remember that a protein is at least 50 of these amino acids long. So if I've got something I can work with, then some amino acids can start further up the chain. If there's nothing down there I can work with, then I just have to work with those two carbons. And they got to start further down. The closer to the beginning that you can start, the more ATP that you can make. The further towards the end that you start, the less ATP you can make. So this is why it shows that proteins enter at a bunch of different stages because amino acids, it really depends on what's there. Regardless of what's at that R group, whether it's useful or not, I always have to cut off that nitrogen group. I always have to cut off these amino groups, and that has to be dealt with. And cutting off those amine groups is expensive, metabolically expensive, and so it makes it difficult to deal with proteins. But the different food molecules that we eat, we still burn them the same way. They just enter at different stages. We started with sugar because we follow it all the way through. As we said, proteins are reduced to their amino acids, and then it depends on what's at the R group as to what can be done with it. Sometimes it can enter further up into primer phase, and other times it has to just enter straight into Krebs cycle. The further down the line, the less ATP you get. But regardless, we always have to cut off that amine group, and it's always converted into urea. Notice that urea kind of looks like, the word looks like urine. It's because it's what makes urine smell like urine. This is what we have to get rid of. And so again, dealing with A, cutting up the protein, B, dealing with that nitrogen, converting it into urea, is metabolically expensive. So even though proteins are hundreds of amino acids long, it's metabolically expensive to burn them up. And so, you know, if you have to put $100 in and you get $150 out, well, yeah, you got $150, but how much did you have to spend to get it to work? I had to spend $100, so it wasn't that good of a return. That's kind of how it works with amino acids. You got to spend a lot to use them, and so you get a lot back, but I had to spend a lot to get there. The foods that we eat are what we use to build our bodies. We take the amino acids to make proteins, we take the fatty acids and the glycerols and make our own fats, and we take the sugars and we make our own carbohydrates. You are what you eat. The food that you take in is used for energy, and the building blocks is used to build your body back. This is why, the rat in Ratatouille said, well, if you are what you eat, then I only want to eat the best stuff, because I want to be the best stuff. See you in Chapter 7.